Yeah, so it's just that should work.
His.
Yep.
Yep. All right. Cool. Turn that off so we don't have to.
Wait. Okay, so this is so I'm Michael Colomb. I'm currently a fourth year grad student at MIT, and I'm here to talk about shared experiences, which is my story of using D and building a shared data structure, where shared is explicitly the keyword shared in the D language. So I'm going to start with a quick background about me, and then sort of detailed look at exactly what shared is and how it works and how it's defined. Then I'm going to go over merge array, which is the data structure that I developed in D for my master's thesis. And in the context of everything I talk about in that, I'll get into some of the neat things I learned and some of the problems I noticed or had with it, and conclude with that. So basically, in summer of 2011, in undergrad, I ended up working on some research, and I coded that in C++, and there were a lot of trouble going on with that and I wasn't using super advanced C++ features or anything, but there were a lot of tension when I was going through that, and early the next year on Reddit, I noticed that there were D posts being posted on the programming subreddit, and that led me to the D forum and everything, and reading about it, I really liked what I saw. I noticed that a lot of the code that I'd written in C++ during that research felt like I should have written it in D because of the way that I was trying to use the C data structures and some of the things that they lacked that I thought were really useful. So then when I went into grad school and actually had more research to do, I actually did it in D, and I liked it. So that's what I want to talk about today. But the first thing I want to talk about is shared. So if you're not familiar, multi-core computers are everywhere, from the smallest computers to the biggest ones. But writing concurrent code for them is very difficult. You have all the normal problems in programming, plus an exponential amount of interleaving that you have to be able to manage when you're dealing with multiple threads running in parallel. So shared basically is having explicit thread local versus thread shared data. And this is beneficial because you have a lot of human documentation, but they also have help from the compiler for optimizing things and protecting you from doing things that aren't good. But you might have heard that shared is a disaster if you read the news group or Bugzilla. So some of the things that shared might have once tried to be or thought to have been, it is not. So if you have a shared data or data structure, you don't automatically get race freedom from your code. It doesn't automatically add memory barriers. It doesn't give you sequential consistency on its own. Doesn't make anything thread safe on its own. What it does do is it prevents certain optimizations that are not safe to do on shared data. It prevents thread local storage so that you can actually share data between threads safely. It prevents you from mixing shared and unshared data in the type system. And there are some compiler guarantees and prohibitions for certain very obvious bad code that you have to deal with yourself. So let's go over some of the properties of what shared really is. So at its base, it's a transitive type constructor, qualifier, and or attribute. So if you have a shared array of integers x, its type is going to be shared int of x. And you can tell that it's transitive because if you take the front of x, then that is a shared int and not just an int. And the reason that you can tag methods with shared and types with shared is so that you can distinguish between the two different types at compile time. So here was struct z, and has a value and a get method that is labeled as shared, that if you create a non-shared z, the compiler won't let you call get on that shared instance, on that unshared instance. And similarly, if you try to mark, a random class type or struct type from the Phobos that's not built for shared, try to make a variable that's shared and try to call one of its methods, it's not going to be a shared method, so you can't call it on that shared object. So the next thing that shared does is if you have a shared expression, you can't use the normal read, modify, write operators. So you have a shared integer, you can't do v++, or v times equals 7. The compiler will tell you that this is depreciated and to use one of the D runtime library atomic operations. Similarly, or not similarly, you can still use the syntax on user-defined types with op assign methods that are labeled shared. That the compiler won't complain about this. One other nice thing about shared, though I haven't seen too much use for it, this particular feature is that immutable is implicitly convertible to shared const. Because if something is immutable, you can share between threads, and you won't ever get anything bad because they can't write and mess up what the other threads might see. And you can see here an example of where this works. You have a shared integer and an immutable integer, and you have a function that takes a shared constant, then both of them can be passed in, and it's okay.
Nice.
So a slightly different way that shared works, and also immutable, is for thread local data. That there's the high-level idea of thread local data, but there's also a sort of concrete thread local storage feature of D on other languages that shared allows you to have control over very easily. So on the left here is a bunch of different types of integers, and you want to consider, how does the assembly look if you try to read from those integers and pass it to something like writeline. And in the assembly here, you can see that t, which is just a normal global integer, has to be loaded from a special part of the data of your memory that's called TLSGD, and the RIP is just a thread. So that I was compiling this with 64-bit Ubuntu 16.04, which has position-independent executables. But that's not important for this talk. So the TLSGD, that's thread local storage general dynamic, I think. Mm-hmm. So it's basically just a part of the memory where basically an index into a thread local storage array exists, and so you use the TLS get adder function to basically index into an array in order to get the actual value of t, and then write it. Contrasting that, if you have a shared integer that's also a global, it loads it directly from the GOT-PCREL part of the memory, which is the global offset table program counter relative part of memory, which basically just means it's a global, and it's not like a thread local storage index. So it just directly reads and passes it into the function without any overhead. Obviously, this wouldn't be thread safe, but this is just an example of what the assembly looks like.
Mm-hmm.
Similarly, if you have, very differently, if you have an immutable global, that's already initialized, compiler can just put that value directly into the instruction. Otherwise, it would just load it like any other, and like Z. So G shared is sort of a strangely underscored notation that allows you to disable the thread local storage without changing the type. So it's not going to be safe, but if you need to deal with extern C variables, or you just sort of want to get around the type system for other reasons, then that lets you have a global, static global that doesn't change the type. So one interesting thing about shared is that if you have an expression that's considered unique, you can, without any sort of casting or issues, have that convert thread local mutables that are unique to shared values, and vice versa. But uniqueness in the compiler and in expressions is kind of hard to preserve. If you ever assign something to a variable, it's not going to be unique anymore. Here are examples in standard concurrency. The send function doesn't know that things are unique when you pass it in. It just sees whether it's shared or not, and it will complain when it's not shared, even though it's a unique thing that is castable. Here's a more complicated example, maybe. So this is a struct that has a pure constructor, and then I have two different types of functions. One where it takes a non-shared pointer to this struct, casts it to shared, and then sends it. And then another function that takes in a shared one and then sends it, just as a simple wrapper here. So if you take the unshared function and you pass it in a unique shared A, then that'll work because the compiler will know it's unique. But if you actually try to call the constructor, then the compiler is going to only allow that to work if it's a pure constructor. Even if internally it's a pure right, code, it requires the annotation or inference. Yeah. Similarly, even if it's shared, even if you don't explicitly construct a shared A here, if you create it just as the init value on the heap, you can pass it in, but if you try to use the constructor, it needs to be pure.
I think there was some talk of making constructors always infer, because you have to have the code for it anyway, because it can't be virtual. But that never happened. I'm not sure if Walter still believes that's a good idea.
Yeah, that would be interesting, because we do it with templates because their code has to be there.
Right.
Yeah. Also down here, I forgot to change that function name to S instead of except shared. But you can see that when you try to assign it to a variable, then the compiler doesn't know it's unique anymore.
Right. Right. The uniqueness is gone after the expression is evaluated.
Yeah. So if you've looked in Phobos, you might know that there's standard types cons unique, which is a template class that's supposed to be able to wrap a type and give you, a value of it that's supposed to be uniquely held. But you can see here that it's the same sort of issues as before, where if you have a class A and you can basically give it anything in its constructor, and it will be able to take that in as its value, even if there are other aliases to it. That there's not really any way for it to require that the constructor takes a unique object.
There's no unique type constructor or anything like that. So it's all an internal thing the compiler knows, and you can't tell it.
Yeah. So the only way that at the moment that you could do something like this is to either have it so the unique type would have to construct the object itself on the inside, or it would have to do like a deep copy of everything.
Right.
Both of which are not ideal.
Pure function as well.
Yeah. Also, one other downside with unique is that it's not. It doesn't mesh with standard concurrency. If you create a worker and you have an actually unique value in a unique struct, then you can't send that unique struct directly or do v.release, which gives you the value and erases the original. In a case where it actually is passing in a unique value, that no matter which one you do, you still have send complaining that it's not a shared value, not a shared thing. But this, in the first sense, it's more of a library problem, because if you assume that the user has to use unique correctly, and you pass in a unique to send could know that a unique thing should be passed on its passed differently.
So
yeah.
It would be possible.
So one other interesting thing about shared is synchronized. So synchronized is the feature where every object has some monitor, and synchronized makes it so everything about each object of that class has to be protected by the monitor. So every method that you call implicitly has to lock the monitor when it enters and unlock it when it exits. All the values that it uses has to be private. But one thing about synchronized is that it really only makes sense to use a synchronized object when it's shared, because if it's thread local, then there's no reason to have the lock in the first place. But actually, the compiler requires that if you want to instantiate this class, for example, it has to be a shared value.
Okay.
But as far as I'm aware,
so it's implicitly shared in the.
Yeah. So it's
all functions are implicitly shared.
Yeah. All the functions are implicitly shared. So that means all the values are also shared here.
Right.
So ideally, and what the compiler is supposed to do is that when you go inside a method, that the data isn't really shared. It was originally typed as shared, but once you go in and you get the lock, you're the only one who's supposed to have access to it. So, if you can see that there's shared int.
Now, what if you
as the type?
What if somewhere you return a reference to the?
Yeah. So so there are rules about. There are special rules for synchronized classes in terms of escaping references. I don't know how.
Unwritten rules or compiler rules?
I'm pretty sure they're compiler rules. They're in the documentation somewhere, but maybe only in the D programming language book.
Right.
But either there are or there should be rules special rules about not being able to escape references, and also rules that maybe might be changed by some of the new developments with scope and return and all of that. I'm not sure.
Yep.
But
because technically it's legal to return a pointer to X for a class because the class is on the heap, so you can do that.
Yeah, well, in terms of lifetime it would be correct, but in terms of the lock it wouldn't be correct.
Right.
So you would need to do something with grabbing the lock and then calling it, and it would have to know that you have the lock. It would only be safe if you already have the lock or something. But
right. Maybe you need some kind of attribute like lock only or something.
Yeah.
I don't know.
But yeah. So one thing. So that. As I said before, doing something like ++ x isn't normally allowed with a shared int, but this is actually something that sort of should this code should be 100% safe and perfectly fine because you're under the lock, the
right.
pointer isn't being shared, but a couple versions of DMD ago this gives a warning, the same warning as if you did ++ x anywhere else. And before that, it didn't give that depreciated warning.
Well, I think before that, type of this was not shared test or whatever.
Yeah, possibly. But this was supposed to work before, and I think it's still supposed to work, but it currently doesn't. It was broken by some change in the way that
Yeah.
things were labeled as shared and but not really shared and stuff. So
Yeah.
yeah. So there's a bug report about this.
Ironically, like view text and things like that are not
Yeah.
shareable either.
Yeah. Well, I get to that here. Yeah. So that's basically what shared is. But let's look a little bit about sort of how it is and can be used. So in Phobos, you have standard concurrency, which is sort of your message passing model of concurrency. So you have the send method that lets you send objects and receive them, but it generally only allows plain old data types, immutable and shared values to be passed between threads. But there's no nice way, at the moment at least, to transfer these thread local values without doing casts. The unique would be nice, but on one hand, it's not always, it currently doesn't recognize it, and it can also be difficult to actually make sure that you're actually sending a unique value, that there are bugs that would be associated with that.
Could STD concurrency be modified to accept unique and understand that? And just you're sending this unique thread local value. But
Yeah, so if you had send have like a special overload for ref unique, thing, and then it would do release to take the value and send it.
Right.
That should be a very plausible.
I think that's a good enhancement request to add.
Yeah, I think that's a very plausible thing to do. I know there's some hesitation, but people wanting to have certain modules have types from other modules because you want to keep them independent. But I feel like this is probably a really good example of that being a good idea. So as an alternative to standard concurrency, there's standard parallelism, where you have tasks and you have some easy functions that let you map across tasks or do something in parallel for multiple parts of a range. But the tasks generally allow for sort of unprotected, mutable, unshared aliasing of values. I have an example here of, if you just do, for each element in some range dot parallel, that's a very easy thing to do, but you're passing in a delegate that has access to the full scope of the current function that you're in without any sort of type checking or other sort of warnings that would allow that to be verifiably safe. There's also core.sync and core.thread, which are D runtime libraries all about concurrency and sharing and protecting data, but almost nothing in any of those libraries is actually marked shared or usable when that object is labeled shared. And there's also can be kind of tricky because mutex is a class. So that means that if you have a shared mutex, it's that the reference and the actual value is shared. If you want to get an unshared version of it, then you can't. There isn't a way in the type system without a special library type that would say it's a unshared reference to a shared value class.
Yeah, it's the head const or head.
Yeah.
No const or whatever it is.
Yeah. So it's the same problem but with shared.
Yep.
Yeah, but one very nice library in D runtime is core.atomic. Basically gives you access to a large variety of lock-free primitives, special instructions in CPUs to allow you to do a lot of really nice things. And it does it in a very nice way. So I'll just go over this really fast, especially since this is the primary thing I use to actually make my data structure. So when you're doing concurrency without any sort of trying to just do normal computer instructions, the main issue you're going to have is that whenever you read or write data in one thread, some of that data is going to, everything you write is going to stay in your cache for a while. Everything you read could be old because the other threads haven't written to it yet. All those sorts of problems make it very difficult to actually have a consistent view of the world. And to solve that, you can use atomic store and atomic load, which basically allow you to write and read values to basically any reasonably sized shared integer or struct with few members. But store and load isn't enough. That it's not too hard to prove that there are actually problems that you want to solve, especially building data structures, that you can't just use store and load and solve this problem. So what D and other languages have is concurrent swap, or CAS, which is a special primitive where you give it the addresses of the register that you want to change, variable you want to change. You give it the value that you expect it to have, and if the register's value has, or if the register has that value in it, then you swap it with the value v that you want to replace it with. And all of this happens atomically in one instruction. And the output of this function is a Boolean for whether you actually wrote or not, and that allows you to branch based on whether you were successful. This is sufficiently powerful to solve any concurrency problem that you want. But it's also can be very expensive, so there's also nicer operations that are also atomic that you can use atomic op for, especially doing a atomic increment. If you try to implement this with a CAS, you're going to end up with a loop, but an increment can be more efficient. Use its own specialized instructions if you support that. So without all that, now I want to talk about merge array, which is the data structure that I built using all of these things. So merge array is a mergeable priority queue. So what a mergeable priority queue is basically something that would satisfy this sort of interface. If you have PQ0 and PQ1, you can insert values into a priority queue, and you can merge two different priority queues together. And when you merge the two priority queues together, all of the values that you put in either one end up just in one single priority queue in the end of the merge, if you get a success at least. So now what you can do, since it's a priority queue, the idea is that you want to remove the minimum value that you've put in. So since I've inserted here 0 through 9, if I do a remove min, I get 0, and then I do a remove min again and I get 1. And you see I do it on the two different references, but I'm referencing the same object and removing that value from that object. And if you try to merge two references that actually point to the same priority queue, then the merge will give you a different value that were already equal, to show that it failed because they were already the same.
So basically merge is taking all the values in this priority queue, putting them together, and then making both point at that same data structure. Okay.
Yeah. So you can define merges differently, where you would you would just move all of the items from one into the other, and then just leave the other one empty or invalid in some way. Mm-hmm. But I found that this was the better way to define this, more convenient way to define this. Yeah. So if you forget concurrency for a second, there's a variety of different variety of different options to choose from. It's not too important, all of the details here. Some of these are very good practical heaps. They're usually called heaps when they're mergeable priority queues. Pairing heaps and skew heaps are both very practical. Fibonacci heaps and Brodel queues and stuff have some better theoretical guarantees, but aren't always very practical. But we want multi-core. We can't just have a sequential priority queue. We want to be having concurrent priority queues. So this is basically what we have for concurrent mergeable priority queues. It's nothing. And it's very strange when you have so many different options here, but nothing here.
Right.
So there's the question of why is this, and what can we do about it? So if we think about what a concurrent mergeable priority queue should be like. So here you have a shared priority queue, PQ0, PQ1. So this is basically code that works with the data structure as I've written it. The higher level things could vary. In this case, each of the priority queues, it knows how many threads there are, and it has an index to know that they're different, to know their index. So you initialize the queues as empty. So if you create your number of threads, each of them with an ID. The way you can do is, insert their IDs into PQ1, merge PQ0 and PQ1, then they can do a remove to get an ID out. I'll explain why it's remove any later. But
why do you have to merge the?
Yeah. So this is just an example program.
Okay.
Yeah. Inside the for loop are the three main methods that you have for a priority queue, mergeable priority queue. Yeah. So. So this is it may look very nice, but we want to know what this is actually supposed to mean. So the first thing we want for a concurrent object is for it to be linearizable. And the basic idea of that is that when we have these three methods here, that we want it so that each method executes as if it happens in a single atomic instruction. It won't actually be that way. But the idea is that at a high level, it looks like it behaves that way. If you have two methods that run at the same time, there's always some point during each method that you can say is when that method actually happened. And that gives you a linear ordering of everything that happens that you can reason about as if it was a sequential execution. So it's very useful for not only designing something because it's a very nice property to have, it's also, if you have two different linearizable data structures, you can use them both together in a program, and it's still linearizable, so you can still reason about it. Mm-hmm. So that makes it very easy to use linearizable objects as well. So that's the first sort of design goal. The second one we want is lock freedom. So the basic idea for lock freedom is that when you have a thread enter one of these methods to try to execute it, that a thread can never get stuck in that method waiting for a lock or waiting for someone else to make progress or anything like that. It might be possible that if one thread is running but other threads are constantly making more progress in sort of, whenever one thread wants to do something, another thread does it instead and it has to try again, that a thread could still get stuck doing something like that. But it's always the case that there's some threads that are making progress all the time, no matter what. And if you want to have good, efficient parallel code, you don't want to have threads, getting stuck forever, having to depend on the scheduler to schedule threads in a certain way such that they're able to make progress, and they might not if you don't have a good scheduler. So the last thing is scalability. So if you increase your number of threads, you want your program to get faster.
Right.
So if you do lots of different inserts and merges and removes with more and more threads, you want to get a benefit from that. Otherwise, why are you investing in a multi-core computer in the first place? And being scalable is different than being simply efficient. If you compare the code for merge array here with just a skew heap or a pairing heap, it's much longer. Things takes a lot longer to execute each method. Has to touch a lot more data and use a lot of slower instructions to be atomic. But since it's able to be parallel and scale, then that's where you get the win.
Right.
But obviously you do want to be as efficient as you can in general. But yeah, so so this is a very nice thing to have. So why don't we have it yet? So I think concurrent mergeability and priority queues is sort of a unique combination of challenges that makes it very difficult. So it's a priority queue, so that means there's only one minimum value. So if you have lots of different threads coming in trying to remove the minimum value, they can't all take the same value. They have to sort through all the top values, and there's very few of them compared to the number of threads. So there's a lot of contention there that can be very inefficient. And sort of the opposite problem is if you do a merge, you basically have to move everything in bulk. And depending on the way the data structure works, you might not have to touch everything in the entire data structure. But you basically have to logically affect everything and where it is and how it relates to each other. And obviously the big challenge is that you want it to be fully asynchronous, scalable, linearizable, lock-free, all of that. So that makes it very difficult. So what would be one good way to deal with having very harsh restrictions? If you hazard a guess.
With these harsh restrictions?
Or in general?
I'm not a lock-free type person, so I would probably just use like a mutex. And it would turn into one thread instead of multiple threads. But that's, I don't dabble in this stuff, so.
Yeah, well, the main thing I'm trying to get at here is that what you do is you relax your restrictions. So some of the inspiration for this, for merge array, comes from some of these concurrent data structures that are relaxed. So the K-FIFO queue, for example, it's like a normal queue, except that there are holes in some sense in your linked list of or circular array of items, and the queue allows for out of order inserts and deletes of up to K slots. And using that, you can have a lot more threads, insert and delete at each end in parallel, and get a lot of efficiency. There's also the spray list, which was developed by other people in my group. So I don't know if you know what a skip list is. It's you basically have a linked list, and then you have another linked list that gives you a shortcut basically to every other node.
Okay.
And on top of that, you have one that gives you to every fourth node, recursively, sort of as high as you need it. And to make this efficient and parallel, rather than doing it very evenly spaced, each node basically is a little tower with lots of different pointers to the next nodes, and they're all sort of randomly random heights. Very nice, efficient way of having a sorted list, basically. And having a sorted list gives you a priority queue because you can just take from the beginning, and that gives you the minimum of sorted list. So the spray list is basically you have that, but when you do a remove, rather than just taking from the first one, you do a random walk with certain constraints, sort of in the first section of the list, and take from there. And since you can have lots of different threads go to different places, you can get a lot of concurrency out of that, some other benefits. There's also the multi-queue, which is more related to merge array, which is basically, instead of just having one queue, you have an array of queues where each one has a lock. And each thread sort of randomly chooses an index in the array, tries to lock it, and then take the item off the queue, or put one on the queue. When it removes, it does a similar kind of thing. And looking at these sort of objects, that there is some demonstration that having a relaxed data structure like this, because you're losing some of the ordering guarantees of a priority queue or a normal queue. But when you're in a concurrent setting, there's a lot of unknowns with the way that things are ordered in the first place. If you have two threads trying to remove from a queue, if
so the first thread to actually remove something might not remove the actual minimum, but the other guy's going to remove the actual minimum.
Yeah. So if you have
it might be a little out of order, but it's okay because you can't tell the difference when you're looking at it.
Yeah. I mean, the primary thing is that either you can't tell the difference or the difference isn't as important to the application all the time,
right,
since it's so unpredictable,
okay,
non-deterministic. So even though it might seem like I have to be delayed by k in terms of getting the actual minimum or the actual first item of the queue, but it's actually, if you have a lot of threads banging on the queue, it doesn't really matter if a thread gets the fifth one. If there's 50 threads all trying to get them, it doesn't matter where it was in the ordering, in terms of the real the clock time that it got the item. So now I want to give sort of a back of the envelope merge array overview here. So the idea for merge array is that you have PQ1 and PQ0. Those are both basically just pointers to a node, which is a handle to a bag, which is an array of normal sequential priority queues. And PQ0 is the same thing. These nodes in the middle, they each have an ID 0, 1, so they know that they're different, and that there's one can go before the other in an ordering of their IDs.
Mm-hmm. Where's the ID come from?
So that's back at the beginning here. So there's 0 and 1. So you pass in the ID when you create it.
The ID.
Yeah.
Okay.
Yeah. So each priority queue when you make it has an ID. The ID goes on the handle node.
Okay.
Yeah. So if you want to do an insert or delete, what you do is you start at your pointer, you follow it to your handle. If that handle isn't pointing to anything else, then you follow the pointer to the array, the bag, and then you can randomly choose an index and then do an insert or remove.
Mm-hmm.
And that works for either one. It's the same. So then if we want to do a merge, the first thing that you want to do is connect the handles. So when you have this pointer from number 1 to number 0, that's telling you that the number 1 bag is going to be merged into the number 0 bag. So if any thread, or if you go through the PQ1 handle and go to that node, you see that there's a pointer going down, you know that there's a merge happening, or that you should just follow it directly because the merge is done. Mm-hmm. So the way the merge works is pretty straightforward. You take each priority queue, index by index, and merge them in a sequential fashion in there. And you merge them all until the one that you're taking from is empty. And then to finalize this, you erase this pointer, you nullify this pointer. So now anytime you go through the PQ1 node, you see that pointer is null, so you know that you need to follow it instead. Follow the pointer down instead to get at the items that you want. And once that is null, you can erase some other things. You can update your PQ1 handle to just go directly to the 0 node rather than the 1 node. Mm-hmm. And you can also now garbage collect the bag or the one node. There aren't any references to it. Yeah, so this is basically how it works, how it would work in a sequential setting. Getting this to work concurrently is much more complicated. But the idea is that you get scalability because you can have many different indexes in this array where each thread can do its own local work. If you want to insert 50 things, you have a 50 length array. They can all do an insert at the same time as long as they find out where they're gonna go.
Ali Shirelli, you've heard of him, I'm sure, right?
On the news group?
On the news group, or his deprogramming book.
Okay.
Has a question. It says there are 2 pointers, only one of which is used at a time. Is that essential for lock-free?
So the pointers, so they are used at the same time. There's sort of 3 different states of them. Sort of the default state is when the pointer that points to the array has a value, it's pointing to an actual array, and the next pointer that goes down is null. So that means that that the handle node that you're at isn't being merged into something else at the moment, and that it's okay to go to the array and do something, do an insert or delete. When you get into this state, and a thread, you can see that both pointers are active. That means that there's a merge in progress. So you know that whatever the current pointer to the array is being merged down to a node that doesn't have a next pointer that's somewhere underneath it. And when you're done with the merging, you nullify this pointer, and that tells you that this handle node has been merged into something else and doesn't matter anymore, and that you should go down instead.
Right.
So those are sort of 3 states of these handle nodes that deal with the way the merge works.
Now we still have locks, right, on the individual.
Yeah, so there will be locks on the different indices, and I'll get to how that works with lock freedom and stuff. Yeah. So this is a cleaner diagram of what it looks like in the full concurrent setting. So the red and the blue are 2 different index handle nodes at the top, and then they point to their array with the bag pointer, and then each place in the array has a struct in there that has a lot of different data. One of that data is LM, which includes the sequential priority queue and a lock to protect it. So for doing a concurrent merge array, we want linearizability, lock freedom, and scalability, and a rough correspondence to the solutions in order. That the first thing we do is relax the remove min ordering, where you can just go to any of these positions in the array and do a remove, rather than having to look through every single one and try to find the minimum or something. The next big thing is that rather than trying to steal each heap from one array and then move it into the other, and then steal it and move it and steal it and move it, what you do is instead have a lazy merge list. So you can see here there's a head pointer on each of the cells here in the array, and that is the list of correspondingly indexed cells in other priority queues, other bags, that are going to be merged but haven't been merged yet. And if you follow the blue node's head, it has a list that all has blue arrows. the red node has its head pointing to the blue node, because the blue node is in the red node's merge list. And the rest of the red node's merge list is followed up in the upper next pointer of the blue node. So it's an intrusive linked list. And that goes down the red pointers for the rest of the things that might be needing to be merged into the red node. And you can see at the very top that the blue node is being merged into the red node. And that's why the blue node is in the red one's merge list. Yeah. And each node also has a parent pointer, so it knows what it's being merged into. For a variety of reasons, it's nice to be able to have a back pointer during all the different algorithms. Yeah. So this is the basic call graph structure of all of the different pieces of merge array. So the priority queue and skew heap in the middle here, that's sort of the user code that someone who wants to use merge array as to build their own data structures that may or may not be a priority queue even would use. So priority queue, there's a merge method, there's insert, there's remove any, and there's also try remove any, because try remove any would let you bail out if you don't want to wait for too long to get an item. And at the bottom here, you have a sequential skew heap with a delete min, insert, and merge steal, which is like what I described earlier, where you take all of the items and leave the other one empty. And that's because that's what you want to do between the different indices. So inside the actual sort of implementation code for merge array, there's the handle, which had the indices that connect things together for merging. And then there's the bag that handles the array and the elements of the array. So the basic idea for a merge, for example, you start in the priority queue of merge. So then that basically calls straight into so it goes straight into the merge into for the handle, and that method is about connecting the next pointer of the blue node, for example, with the red node at the top. The first thing it needs to do is it has to go through a descend merging function that if you have a long chain of these handle nodes that are all trying to merge into each other one at a time, trying to merge two things that might be completely different, but one of them is supposed to end up at the bottom of that list, you need all of the other ones to finish first. So when you go through this descend merging, the thread will help those other things finish before it does the actual work that it's going to do. And either way, both merge into once it's at a point where it actually made the next pointer connect to start the merge process. It goes to a method that's called ensure merged into, which then actually follows the bag pointer of the node that you're trying to merge out of, which is the destination, and then the node you're merging into, which is the source, and to insert each index of one into the merge list of the other. Because each index has a struct in it with its own list.
Right.
So from each index in the destination, you need to add that node into the list of the source node. And you do that. You do that one at a time, and that can be done by multiple threads in parallel. And that is done in the merge per element into, which has a loop on the inside to go over the different indices, and different threads can start at different places and try to finish everything together. And other threads that are in the descend merging method trying to help it finish will also come and help it finish. Yeah. So then, once you've inserted all of the nodes in the source into all the lists in the destination, then the merge is done. You don't do anything else. So the merges are lazy. That's why the merges are lazy, because you don't actually evaluate them until you try to apply one of the skew heap methods to do inserts or deletes, for example. So if you're going to do an insert or a remove any in your high-level priority queue, there's sort of a generic apply and apply until method. That takes in like a delegate and gets you to a state where the thread is given one of these heaps at one of these indices to apply its method to. And the way that works is that the public apply just goes to apply until, because apply until has a predicate and apply is just a convenience function. Mm-hmm. So that goes into a try apply until in the bags internals. And that gives, in there is when you're looping, is where it loops over the different indices to try to apply it at each index. So at each index, you can see the lock symbols here. Those represents where you're trying to take the lock. But because we want something like an insert to be lock-free, we never actually use the lock method. We always use the try lock method. So the try lock method will never wait for the lock to wait for a thread holding the lock to leave. If the lock's already held, it's going to stop and tell you that it was already held. And when that happens, that means you can go try a different index. Maybe that index won't be locked. And if you have enough indices for every thread, then you know that there's always going to be some index where any thread can go and get the lock. And that means that any thread that's trying to get one of these locks, there's always that the only way it can be like constantly failing to get a lock forever is if other threads are constantly stealing it first.
Right.
So that's why you have lock freedom for something like insert. I mean, everything else has to be lock free too, but the reason that you can have a lock free insert is because if you have enough indices, you can only never make progress if other threads are making progress and blocking you.
Which is still progress.
Yeah, exactly. Yeah. So, the high level idea for how the, so the try apply until it tries to get the lock. If you do get the lock, you're not done yet because you still might have a whole bunch of merges that haven't been done yet. So you have this giant merge list. Every node in your merge list has its own merge list, recursively, possibly.
So you'd have to go down and merge all those, but you don't have to lock those to merge them, right? Because it's just like once
No.
you've locked yours, you.
So the lock at the top doesn't lock everything else, because even if, so one thing about like all of this, in this state here, if a thread, so say a thread is in PQ1, it goes to the handle, it sees there's not a next, it goes over here and goes to index 1, and then some other thread does this, and now that thread is still at index 1, and it still wants to try to do work there.
So you still have to lock that.
Yeah, you still have to lock that. And remember that all you're doing is inserting into a list. When you're doing this, you never take a lock when you insert into a merge list. If you follow the merge arrow, it never goes through a method that's taking one of these locks.
Right.
It's completely lock free and lockless. So any thread that wants to try to take the lock and do work is still able to do that while a merge is in progress. So you have to take these locks to make sure that any thread that might be trying to do work there, you're not just going to try to steal everything from under it, and because that would be unsafe. Because the idea here is that you want to take all these sequential mergeable priority queues and put them all together in this structure to get a concurrent one. So you need to keep those sequential. So you can see that so the try, eval, merges, and apply, it basically, you have the lock. If you get the lock, then it goes through the merge list in eval merges locked. It goes through the merge list for each one. It recursively locks that, and then calls eval merges locked on that. When you get to the bottom of one of those things that doesn't have a list anymore to merge, it will be able to take the heap and merge it, actually do the merge into the one level above heap. And if it ever encounters that one thing is that because you want to be linearizable, if you have a node in your list where its merge hasn't finished, because there's other nodes that still haven't been inserted into lists, then you can't merge it into your element, into your heap, because the merge hasn't happened yet. If the merge hasn't actually happened yet at a high level, then you shouldn't be able to see it if you try to do a remove. So what you have to do in the bag is you call back up to ensure that it's merged before you try to steal the items. And that is basically just calls into the whole helping merge mechanism.
Did you release the lock for that?
You don't release the lock for that. But it's also true that when you're doing the recursive lock getting, if you're always still doing try lock.
Yeah.
So if you ever fail, what you do is you just sort of bail out all the way up and try a different index at the very top. Because, if somebody's all the way at the bottom there, you're not going to be able to get it again if you just try again. And you need it to be done in order to do anything.
Right.
Yeah.
And you have to, so when you're merging multiple priority queues or heaps together,
Yeah.
you have, this heap has to go with that, they have to be aligned. It's not like you can take from random heaps or
No.
assign this one to that one. How do you keep them balanced? Or does it matter even?
So that's a sort of future work kind of thing. So there are ideas of things where you can it's difficult to, if you wanted to do some sort of random shuffle every time you do a merge, that can be hard to coordinate what shuffle you do. Because you'd have to allocate extra memory for that and have some threads decide on how that works. And that doesn't necessarily guarantee that you're going to get a good shuffle that balances things. I think one of the promising ways of doing it is that you occasionally want to try to lock two things and then shuffle them sequentially and then put them back. And if you do that with all different pairs, the thing can sort of stay shuffled on average. But the current way that this works, sort of in the hairy details, it doesn't really work well if you try to lock two things at once.
Okay.
But that is a problem that I hope to solve in the future. Yeah. So for the merging, you do this recursive merging on all the different lists. If you can finally help all of them finish merging and consume the whole list so there's nothing left, then you know that the heap that's at your top level is what it would be as if all of those merges actually happened, all of the other operations have actually happened. So you can apply your operation and it will see what it should see in a linearizable world. And that goes through a delegate or something. So it can branch into any sort of heap method or other code that wraps it in a priority queue. And there's a lot of flexibility. So for example, for delete min, if one of your slots has a heap that doesn't have any items, you can't get the minimum because there's nothing to get. So you have to return false, try a different index to see if there's an item there. So then you would try a different index at the top and so on. Yeah.
Cool.
Yeah. So the details of getting the merged list right, it took a long time to get through all of the details and lots of testing and assert errors and stuff. So yeah. So I'm gonna briefly go over some of the actual code for how these interfaces work.
I just want to tell you, like, I think 10 minutes before they close.
Yeah. Yeah, it's been about, yeah. Yeah, so maybe try to, because I still have a decent amount more, but, yeah, so you can see here, it's basically what I talked about before. Try remove any returns a nullable, remove any returns the actual value because it has to return that. I have a lot of template parameters here. So you can customize what sort of allocator you use for all of these different things because you have to allocate memory at the beginning. When you make a skew heap, you can use any other sort of priority queue at the bottom or even something that's not a priority queue if you're using a different thing.
As long as it supports some kind of...
Yeah, the only required operation is the merge steal operation.
Yeah.
Everything else is fully configurable. I also have an empty function that's more complicated, so it's an optional parameter. Yeah, so the priority queue thing itself, which is what someone might want to, if somebody else wanted to use the merge array code to make their own data structure, so this is an example of how easy that is. So at the top here I have some aliases to create the handle and the merge array, which is the bag with the array in it. So there's, for the handle, there's a static make with the allocator function to create the handle and the bag and everything, to allocate all of that stuff. And to do an insert, all you need to do is, the handle, which is your pointer to the node, just do dot apply, you pass it, you pass in a delegate that takes a pointer to your inner priority queue, and you just do the insert, and that's it. And, it handles everything else on the inside. So if you want to do remove any, which is the one that it won't return until it gets a value. So you only want to call this if you know there's still a value. So what you can do is you have apply until, so you return either true or false to say whether you want to stop or not. So you do delete min on your priority queue, on your sequential priority queue. If you got a null result, then you would do continue. If you do have an actual value, then you return it through the delegate's context pointer, and then you return it at the bottom there. And it handles everything else. Try remove any, which is the one that is able to escape. You can pass in like a max retries value, and it keeps that as a value that this delegate is able to reference and count down to 0 if it gets too many empty heap things. Otherwise, it's basically the same. Yeah, and to do a merge, there's just the single merge into method. The merge into method requires that you do like an atomic load on your pointer to the handle node because you want to have thread local versions of that. So there's this unshared that just wraps an atomic load basically. And there's also these update methods that changes the pointer to follow the next pointers all the way down so that you don't have to follow a giant list every time.
Yep.
Yeah, and the merge, it returns an enum that gives you whether the merge was a success, whether they were already equal, and then two different types of errors that might come up that should never happen. If you have two priority queues that have the same ID, then you don't know which one to point to which one. Also, if they're different widths, if the arrays are different sizes, then you can't match them up one by one.
Okay.
So those are just different bugs that someone could have. Yeah, so the handle, there's apply and apply until, which just takes scope delegates, which allows it to be no GC if the templates, if everything is inferred properly.
Brackets in the bottom?
I have it like that just because I have a shared version that does an atomic load and an unshared version that doesn't, basically, just so you don't have to do it yourself.
All right.
Yeah.
Okay.
And then there's the handle methods that the bag calls that are package, labeled as package rather than private. Then the bag itself, it has its own methods that are also relatively simple. Maybe I'll skip over some of the benchmarks. So I wrote this back in 2015 with D 2.066.1. I did it with GDC, and data structure I was comparing it to was written in C. So I was able to just link it very easily. And I didn't use the garbage collector. I'd have my own bump the pointer kind of thing. And I ran all this on an 80 thread machine.
80 core.
Yeah, 80 threads. There's 4 processors with 10 cores and 2-way hyperthreading.
Okay.
So that's 80 threads, 80 hardware threads. Yeah. So one thing, because this is a relaxed data structure, you want to know how bad the relaxation is. The basic thing is you can, if you have a sorted list that you can say that the rank error of a removed value is where it would be in that sorted list.
Right.
And you can sort of prove that if you sort of have a very simple sequential execution of inserting lots of stuff and then trying to remove one, that you get if the length of the array is W, you get a W log W rank error. Worst case expected. The average case is just W. And if you look up the coupon collector's problem, it's basically the same thing. So, I implemented a thing in D to actually run it where you have parallel inserts and not sequential inserts. And see here the blue line going through all these centers is the theoretical value that you would get, the W log W. So this is W, this is W log W, W is 80. There's 80 threads. And you can see that the black box plots are the tests, the experimental results, basically matches perfectly with,
Nice.
It basically matches the sequential results, even though there's lots of parallelism. I also ran an actual algorithm to compare it with the spray list, using a different algorithm, but for the same minimum spanning tree problem. So I have some D code for this. The basic idea is that in terms of the runtime for a relatively large graph, my algorithm, which it uses the merges, so the spray list I'm comparing it to that can't merge has to use a different algorithm because it can't use the same algorithm. So mine is like 11 times faster, and sort of as you get lots of threads. But because it's a sort of more relaxed data structure, sort of the quality of your minimum spanning tree, because it's not really minimum, it's an approximate, it's a relaxed minimum.
Minimum-ish.
Yeah, it's a small spanning tree. So the quality of the weight of the spanning tree that my algorithm returns, it goes up relatively linearly with the number of threads, whereas the other algorithm is able to keep the weight a lot lower, a lot closer to the optimum. But it's only like 4.59 times heavier compared to the 11 times faster. So depending on what your application is, that could be, if you don't actually need the smallest spanning tree, you could get a lot of win there. So I'm going to go over some of the things I found. So I had this nice little one-to-one thread mapper, because if you do if you do parallel from standard parallelism, you can sometimes, if the thing you're running is small enough, it can run the same thread on different indices basically in the range. So I had just like a simple wrapper that makes sure you do one-to-one thread mapping. So I use lots of different assertions all over the place in my code. I thought that assertions and in and out blocks were really helpful for actually developing, especially since there's a lot of things with trying to make sure that your state in the shared data that you're working on is what you expect it to be, making sure that your assumptions are met.
I found the same result when I did the red-black tree.
Yeah.
Just doing invariant, saying, is the red-black tree property still there?
Yeah.
It's hugely valuable.
Yeah. I thought this short little bit of code was a nice example of a lot of different features that was very compact. So this is the handle node. Mm-hmm. Like this is literally all the definition for that node, and how it works. So there's the generic handle that takes any sort of bag. I have private, I have align, static shared node, so that the shared applies to the node and it's static, so there's no context pointer. It's a recursive thing. I get to say equals null everywhere so that it's nice and default values. I have an immutable ID for each node because you don't want it to change, and that means I don't have to do an atomic load just in case, or casts or anything. And then the handle, the only data inside is just the shared pointer to one of these nodes, which is null by default. And depending on whether the handle itself is shared or not, you have head shared or not head shared. It was also I'm still not entirely sure what allows the template back and forths to work for my data here. Because the priority queue, it has a handle with the merge array of the priority queue. The handle has a pointer to a thing that has a pointer to the bag. But then the bag has a bunch of back pointers to those handles that have pointers to them and stuff. So none of them is sort of strictly containing a value of the other type. But I thought it was nice that I was able to have these back references and that the templates all worked. I also was able to do just some static values for sentinels that meant different things depending on, that aren't, values for pointers that aren't actually pointing to something meaningful, but I could just use an enum that's an address to one of these values and it'll work nicely. The other main thing is that I have scoped locking that isn't using synchronized. So the LM value is this course locked thing. It has a try locked that gives you the object, and then it lets you do whatever you want. And I have this, so this is part of the, going through the merge list and evaluating things. This is the part where it's recursive. Mm-hmm. So you have the current element you're looking at in your list. You do try locked, and then you do the recursive call on that node and your current node there, and then if it returns that it should bail out, then it bails out. Otherwise, it does the merge steal, and then here at the end is one of the conditions for bailing out. Yeah, so I basically have this, just a test and set lock basic thing with these, lock and try locked methods, and you wrap them in this course locked object that takes in, a value and a mutex and is able to pass things through and do all the casting for you. So it's all very nice. And also, so some of the issues, I guess. So this, so here in the merge array, there's an array of nodes, a slice. Because the width of these arrays are fixed, it's okay to do indexing. But it can be difficult maybe for because a lot of the different operations on slices are working on the two different parts of the slice, the pointer and the length.
Correct.
So for example here, if you just tried to assign a new array to a shared int, if you're down at the bottom, you're writing the length and writing the pointer. Those are two separate operations. So for something like this, you wouldn't expect this. Like this is the same if you do it for any other type that's shared, that it'll try to assign to things without doing special instructions. But there's also like if you just try to index into a shared array, you get bounce checking. But what it does is it reads the length, it checks that, and then it reads the pointer. But if the length has already changed and the pointer isn't, the length and the pointer aren't what you checked, then you can still get issues. Also, the length and pointer properties aren't sort of normal fields for slices. If you try to just assign length equals 2, you end up calling the _d_ array set length t, which acts on it as if it's not shared, and just it reads the length, it tries to duplicate stuff if it needs to extend it, and it reads stuff and shrinks stuff. It's not thread safe at all. And the compiler doesn't warn you about that or anything.
Nope.
Also, you can't do like x.length.atomic store because it's not a R value. X.pointer also doesn't seem to be an R value if I try to do atomic store to it.
No, but you can cast it to
A reference or
the
something?
actual struct that it would look like.
Yeah.
And do stuff with that.
Mm. Yeah, I wouldn't know.
That's actually
like,
what the
yeah.
code inside like the array set length t
Of course, yeah.
is going to do anyway. So you could override that and just do it that way.
Yeah, but if you want to be really simple and portable and stuff, then yeah. But what you can do is if you just do atomic store on the whole array itself, if your machine has the proper instructions of doing 2-pointer length atomic operations, then that works fine. But obviously you have to do any copying or length verification yourself.
Right.
Yeah. I guess I want to end off with talking about like if you look at different sort of lifetime and visibility properties in D, there's shared is among them. So there's immutable and const, which means that you can't write. Shared means that there's concurrent access to the data. Pure for functions means there's limits with the origin of where that data can come from. If you use ref, that allows things to use data without actually owning that data. With scope, you get guarantees that if you can access something, that there has to be some sort of liveness during the scope of that accessibility. And then there's sort of the new return thing where that allows you to preserve lifetime as arguments and return values of functions. But there's also different properties that don't have annotations. Mutable and thread local are sort of default states that are just the negations of immutable and shared. But then there's also uniqueness, which is sort of a real thing in the compiler, but there isn't any sort of way of taking advantage of that in the language in terms of annotations. So there's, typecon's unique. It is sort of nice if you assign, one unique thing to another unique thing, it'll null the first one out, stuff like that. But, it doesn't work with standard concurrency at the moment. And there's, sort of usual template issues that you would run into with other attributes. And there's the lack of it to be able to make sure that what you initialize it to is actually unique in the first place.
Right. Just to make an assumption on something.
Yeah. So for the compiler, there's already stuff in the compiler that tracks uniqueness. That's why you can, exchange thread local stuff for shared stuff. That's why you can have pure functions return something that it changes. But it doesn't work for variables. It only works for expressions. Once you assign it to something or pass it as an argument, then that's lost.
It's only inside an expression. It doesn't pass statements.
Yeah. So, I know there's been a lot of talk about this in the past, but I still think it's a valuable thing to think about. because there's a lot of work with like scope and ref and return, trying to make that work with different sort of lifetime safety stuff. And that something like uniqueness would definitely be able to fill in gaps that those properties aren't reaching. There's languages like Rust that are doing a lot of experimenting with this sort of way of programming and usefulness of it, compared to a couple of years ago when it wasn't as mature. We also have a lot more type inference and attribute inference and stuff nowadays. But obviously, if we wanted to add a new annotation or try to mix other things up in some way that might look like uniqueness, that you can definitely have issues with readability in terms of documentation.
Attribute hell,
Yeah.
basically, so many attributes combined together.
Yeah, so summary is that concurrency is hard, but shared isn't actually a disaster. It's not so complicated and can actually be very useful. I thought that shared and many other features of D were very attractive in making this project happen and continuing to use it in future work. And I think that shared could be a really great feature, greater than it is. If we can sort of clean up some of these issues with casting and library compatibility and all of that, if that can be supported and supported where it needs to be supported in all different parts of everything. So that's it.
All right. Thanks, John. All right.
Yeah. That's the end of the live stream.
All right.